Okay, good morning. Welcome back. Today is Friday the 10th, class number 7. Today we're covering something called integration by substitution. Quiz number 2 is due today, but I will talk about what it means if you don't have it. Project number 2 is due on Monday. Also on Monday, I will hand you project 3. Wheels on the bus go round and round. Questions on the calendar? Okay, and let's jump in on this page here. Daily summary. In this class, we learn the technique known as integration by substitution. We will learn many techniques for finding antiderivatives this semester. The most widely used of these techniques is the one we covered today. In the same way that the chain rule allowed us to differentiate many new functions last semester, the substitution method, that's this one for today, will allow us to anti-differentiate many new functions this semester. Spend time in the coming weeks reviewing this material from this section. This is really important, today's lesson. Okay, number 2, it says let's find the integral of x times the square root of x squared plus 1 dx using the u substitution method. Don't worry about frantically writing out all the steps. The step-by-step process is on a reference sheet near the beginning of this packet. We'll glance at it in a little bit. Okay, this integral is a product. It's got x, and then it's got this other thing, right? Can I pull the x out in the front? Can I take that? No. I can only take the constant out. Can I write x, that integral, times another integral? No, this is not a thing. You cannot do that with multiplication, right? You can do it with addition and subtraction, not multiplication, not division. So, so the fact is we're kind of stymied with this thing right here. And so we're going to do this technique called the u substitution method. So here we go. We're going to let u equal the stuff in the parentheses. Later on, we'll talk about why this is the right choice for u. We're going to rewrite this integral as something hopefully simpler, but it's going to involve u's instead of x's. That's the idea. We're going to take a derivative of both sides of this equation. What's the derivative of x squared plus 1? 2x. I could call this u prime. I'm not going to call it u prime. I'm going to use the Leibniz notation, and we're going to call it du dx, okay? So there's your derivative. I'm going to solve this equation. I'm going to treat this du dx like a fraction. And so I'm actually going to multiply both sides by dx. It seemed a little bit strange, but it turns out to be useful. Okay, so we multiply both sides by dx. And we are going to solve for dx. Solve this new equation for dx by dividing both sides by 2x, okay? So dx equals du over 2x. That is not what I wrote. Wait, du over 2x, yeah, good. So we've done a lot of manipulation. We've got this u, but we haven't done anything with the integral. So it's time to go back to that original integral and see if we can make any more sense of it in our new letter in u. I'm going to give this guy a name. I'll call it I for Ian, or possibly integral. And we're going to replace. So over here, I'm going to say that I is equal to integral x squared plus 1 cubed. What is that really? Can I change that to something else? That's really u cubed. Agree? Okay, that's u cubed. So I'm going to put the u cubed here. I'm going to put the x there in the front. That's just hanging out. So we'll just change the stuff into u, and that's fine. But then instead of dx, well, I've got another version of dx down here. It's du over 2x. Du over 2x. So I'm just going to highlight the 3 pieces, 2 of which became substituted. Right? X squared plus 1, that became this thing. And then this stuff right here was the dx, okay? Everybody agree that every piece that we had in the beginning is now a corresponding piece in the new integral? Okay, and then we cross our fingers that all of the x's that still happen to be here disappear. And in this case, they do, right? I've got an x here, and I've got an x there. And so that means that my new integral is u to the third du over 2. Agree? And that is an easy integral. That's one of the few integrals we can do. We've got a very small list of antiderivatives that we know, and a power rule is one of them. And so we can handle this integral in u's. Let's finish up. What can I do with that too to make life easier? Put it out front. What does it become out front? Is a 1/2 integral of u to the third du. Make sure when you pull it out front, it stays on the bottom. And then our basic power rule says add 1 to the power and divide by the new power. So we go u to the 4 over 4 du. What do we put out here? Plus c, right? Most general antiderivative we can find. Okay, so this answer is fine. I guess we should smush the 2 and the 4 together to make an 8. But if your final answer said u to the 4th, well, that's kind of funny because the original problem had what variable in it? Was x. U is something we invented to make this integral something we could handle. So then we go back, instead of u, and just use our definition. Yeah, it's right there, right? U is x squared plus 1. So we just change the u to an x squared plus 1. X squared plus 1 raised to what power? To the 4 plus c. And that's our answer. What do you mean? Are you talking about for integrals still, or just in? Oh, yeah, I guess sometimes we use the substitution idea for factoring to make things look a little bit nicer. Mm-hmm. Yeah. Okay. We can check this. I mean, it was a technique and we just kind of followed the bouncing ball and everything worked out at the end. But you can check every antiderivative you ever do by doing what to your answer? Taking the derivative. And we're really hoping we get the original integral, right? So let's take a derivative. We're going to do this in our heads. That 8, does it stay or go? Taking a derivative, that stays. So we're going to imagine there's an 8 in the bottom of our answer. Take the derivative up here. 4 comes down. Copy the stuff. Subtract 1. And then times what? 4 comes down, copy the stuff, subtract 1 times the derivative of the stuff, right? Which is 2x. So in my mind, I've got a 4 in the front and a 2x at the back, and that's 8x. But this 8 was just hanging out here at the bottom the whole time. 8x on top, 8 on the bottom, just x. So x times x squared plus 1 cubed, which is exactly what we wanted, right? Okay. All right, so let's take a quick look at the reference sheet near the beginning of this packet. It's right here, page 8. Everybody jump to page 8 real quick. So page 8 involves a slightly different integral, x squared times 3 plus 4x cubed to the 5th, but it's going to be exactly the same idea. We let u equal some stuff in the parentheses oftentimes. So we let u equal 3 plus 4x to the 3rd. We take a derivative of that. What's the derivative of this guy? 12x squared. Okay, so there it is. We solve that equation for dx every time. We solve the equation for dx, so the dx comes up. 12x squared goes down, and we get dx is du over 12x squared. And then we start substituting. This x squared stays just like it is. The thing that you called u, you better get it in there. So that becomes a u to the 5th, right? And then the dx, in this case, is du over 12x squared, right? And then we cross our fingers that the x's disappear. If the x's don't all disappear, then this technique didn't work. Doesn't mean we made a mistake, it just means we need a new technique. So in this case, the x squareds cancel, right? And we just get integral of u to the 5th du over 12, and that's easy. That's just a power rule. And then don't forget at the very end, after you do your antiderivative, you got to go back. You can't leave your answer as a u to the 6th over 72. You got to substitute back to the x's, okay? So what made this thing here tick is that the derivative of this guy right here, what was it? Just the stuff in the parentheses? 12x squared, which is basically sitting out here, just missing the 12, but we can handle a missing 12 because I can multiply by 12 and divide by 12. So what makes this work is that you let u equal something whose derivative is sitting in the front, except maybe it's missing a constant multiple. That's the key idea. The derivative of whatever you let u equal had better be sitting there in plain sight, possibly missing a constant multiple. There's a table down here for some good choices for u. In the two examples we just saw, we had stuff to a power and we let u equal that stuff. If you have some stuff inside of a square root, you might try letting u equal that because square roots are powers, right? That's stuff to the half. Sine of stuff, cosine of stuff, secant squared of stuff, any of these things here, you just change the stuff into a u and you try it, e to the stuff, a to the stuff. If you've got complicated stuff on the bottom, you can try that. Lots of good choices for stuff. Make sure you recognize that you got this list here as some good options for places to let u equal something. Okay, so we're going to come back to our page, the next page, which is 59. But before we move on to 59, let me just make a couple of quick announcements. Okay, so the first one has to do with quiz number 2. Technically due today, but we didn't have class last time, and not everybody read the email that I sent about Wednesday's class that we missed. So quiz number 2 is the very first page of your packet. You can jump there right now if you want to. So just jump to the first page of the packet. How many folks finished the quiz already? Okay, just a couple. So jump to the first page of the packet. Quiz number 2 is one side. It is just right there, the first page of the packet. It is just plain memorized derivative and antiderivative rules, okay? Like I said, it was due today, but we didn't have class Wednesday, so this will be due for you on Monday, okay? It's another take-home quiz, just like the rest of our quizzes. At the top, the instructions say, do not use any resources. This is just, can you memorize these derivative and antiderivative rules? Now, two pieces of good news for you. Number one, the answer key to this quiz is on the back of that piece of paper. Flip, make sure you see that it's exactly the same thing, but with answers filled in, all right? You can look at the answer key first and make sure you know what's going on before you take the quiz, or you can take the quiz just to kind of see where you are without preparing for it, then look at your answers. Go to page number 3. Page number 3 is another blank copy of the quiz. You can do this quiz as many times as you want. Your best score counts. I'm really hoping everybody gets 100. Flip to the back of page 3. That's another opportunity for you. If you need more, go to Moodle and you can print as many of these things as you want. Keep taking them until you get 100, okay? That's the goal for this quiz. You are going to turn in all of your attempts on Monday. I will count your highest score, okay? You're going to grade this thing yourself, so don't make me work. There's a little spot on the top there for how many you got right out of 38, okay? Any questions on the rules for that quiz? Okay. All right, so that's good there. Yeah, I think that's fine. Okay, so let's come back here to the packet. We just took a look at the step-by-step walkthrough near the beginning. We talked a little bit about this. It says sometimes there's trial and error involved in the choice of u. This is normal and expected. Sometimes you can't see ahead of time what choice of u will work. It takes a lot of practice to get good at this, and I promise I will give you a lot of practice. This technique doesn't always yield a tractable integral. Like I mentioned, if you end up with both u's and x's in an integral after you have substituted, then the u sub you just tried probably won't work. So for example, let's give this one a shot. Remember I'd said if you see sign of stuff, you might let u equal the stuff inside the sign. So in this case, we could try x to the 4th. Remember the next step is to take a derivative. Always use Leibniz notation here. Derivative is 4x to the 3rd. The goal is to solve this equation for dx every time. So imagine two things in your head. The dx comes up to the right. The 4x cubed goes down on the left. Du over 4x cubed. Good? Okay, we'll give this guy a name, I for integral equals integral. Okay, the 2x, we copy. Sine of x to the fourth becomes sine of u. Just always trying to substitute that u in there. Dx becomes du over 4x to the third. And then remember, this is the part where we crossed our fingers and hope that all of the x's cancel. Well, some of them do, right? Get rid of one of these, leaving 2 downstairs, right? If you have u's and x's still in your integral, this u substitution failed. Almost certainly. There's like one special case where it still works, but it's not this. If you have u's and x's still together, it just didn't work. Doesn't mean there's nothing you can do. It just means this did not work. Try something else, okay? All right. Number 7 has this integral, but I want to change that integral. So if you could replace this thing here with the integral from 0 to 1 of x to the third, 2x to the 4 plus 5 cubed dx. Make that change, please. I'm not going to rewrite it, but it's the same one over here. That integral should be in both. Okay, so the only difference here is that this is a definite integral, right? Because there's limits of integration. Okay, so let's give this a shot. So the first thing we do is we pick our u. If you've got some complicated stuff in parentheses, that's probably a good place to start. So what's a good choice for us here? We changed that integral to the thing in the red. So 2x to the 4 plus 5. And just kind of looking ahead to see if this has much of a chance of working, what is the derivative of that stuff in the parentheses? This is 8x to the third, right? And I see an x to the third here. Hey, that's really great because the derivative of the thing in the parentheses is basically sitting here with a constant multiple missing. All right, good. So this is promising. Okay, so we got u equals that. We take our derivative, and we just said that was 8x to the third. And then we solve for dx. Du over 8x to the third. And then we start to substitute. So we called this integral I. So let's give this a shot. I equals integral 0 to 1. And when we've seen a few of these, we start to recognize how the substitution works. Some things get copied, some things change into u's. So what's happening with this x cubed? It's getting copied. There's nothing to do with that. What about this 2x to the 4 plus 5 becomes u to the third? What about that dx? Du over 8x cubed, right? So it's always the same pattern, right? The dx changes, the thing that you called u, that changes, everything else gets copied. Okay, what good thing happens here? I cancel the x cubes, that's great. So our integral is just u cubed du over 8. What can we do with the 8? We'll put 1 over 8 in the front. Integral 0 to 1 of u cubed du. Okay. Most integrals are hard. That one's easy, right? That's what the u substitution is supposed to do. It converts a hard integral into an easy one that's equivalent. 1/8 is there times u cubed becomes u to the 4 over 4. Do we need the plus c? No, this is a definite integral, so this is the one where we go that, right? Okay. All right, so I'm going to smush the 8 and the 4 together, so I'll make a 1 over 32. And then we plug in 1 and we plug in 0. Is that right? and then subtract? What's the problem? Yeah, the 0 and the 1 are not values of u. They're values of what? X. So we got to go back. Okay, so instead of u to the fourth, we are putting 2x to the 4 plus 5 to the fourth. And that is between 0 and 1. Okay, and then we just substitute and subtract. I'm going to put my 1 over 32 in the front of the whole thing. I just think it's easier. So we plug in 1. What's in the parentheses? 7. So we go 7 to the 4 minus. Plugging in 0 oftentimes gives you 0, but it is very bad form to just assume zeros give you zeros. What do you get when you plug in 0? 5 to the 4th. Definitely not 0. Okay. Somebody with a calculator, can you just give us an answer here? All right, so everybody knows 5 to the 4th is 625. 7 to the 4th, 2500, 24, close, like 2401. 2401? Oh. And then 1/32 of that. Okay, so what is this equal to when we subtract? I can't subtract, I can multiply, I can't subtract. 1776 over 32, and then you can reduce it, whatever, I'm done. I ran out of room. Okay, so that's our answer, okay? So that is the right answer, but there is a lie someplace in the middle of this process, and I don't like when my students lie to me, so I don't want you to do what we just did here. And the lie is actually something that we almost goofed on, almost made a mistake right here. What mistake did we almost make? We didn't substitute back. It was really tempting to just plug in 1 and plug in 0 because after all, that is exactly what we wrote. This is a problem. Even though we ended up with the right answer here, this is just not true. If you showed, you know, like anybody who knows some calculus, this thing, they would plug in 1 and they would plug in 0 right here and they would get the wrong answer. They would not get this answer. So what I want you to do is not lie. So let's try this guy one more time. We're going to do it the not lying way. So do it this way for definite integrals. Okay, we're not going to do the entire method again. It's quite similar to the steps that we followed, just one little twist at the end. So we're going to fast forward to the end of this problem. 2x to the 4 plus 5 is our u, right? I'm just going to pause there. That's the only thing I need to copy from the other page. Okay, so this integral became the x to the third and the x to the third canceled, and I think we had a 1/8. Is that right? Okay, so there was a 1/8, and there was a u to the third, and there was a du. This is what we got, and we still have to do exactly the same process. But at this exact moment, putting a 0 and a 1 on the integral is a lie, because those 0 and 1, the 0 and 1 are x's. And so what you can do is you can find the corresponding values of u. Let's do that. X equals 1, u equals, well, there's our definition for u right up there at the top. So we just change that x into a 1. 2 times 1 to the 4 plus 5 is 7, right? And then the same thing for the other x. X equals 0. How much is u? Is 5, right? And so at the bottom, we put 5. And at the top, 7. That is not a lie. That's the right integral. And so I will show you that the end of this part is actually, so this looks more complicated. We had to do more work here than we did on the previous page because we didn't have to do this at all on the previous page. But we get to do less work from the rest of this problem onwards. This u to the third becomes u to the fourth over 4. The 1/8 is just hanging out. And then we're going between 5 and 7, new limits. Do we go back to the x's? No, those are u's. 5 and 7 are truthful numbers for u's. And so we don't substitute back. There's a 1 over 32. I'll just put that in the front. And then we just plug in u equals 7. So we go 7 to the 4 minus 5 to the 4, which is exactly the right answer, right? What we did before. So you could do this the lying way, or you could do this the truthful way. And honestly, I think they're the same amount of writing and the same amount of work. So let's do it the truthful way, okay? For definite integrals, when you do a u substitution, you're changing those limits to the right numbers. Questions on that one? Okay, so like I said, u substitution's most important antiderivative technique of the whole semester. We're going to see more antiderivative techniques in coming classes, but this is the most important one. All right, so the activity is here, recognized in bold. It says find the following integrals, but one of them you cannot do. So don't spend too much time on any one. If you get stuck, check with your neighbors, see if anybody can do it. Otherwise, that's probably the one you can't do.